There's a trolley careening toward a split in the tracks, and you are holding the lever that controls the points. You have a choice. You can either pull the lever and send the trolley up track A, which has the same number of people on it as there are integers, or you could do nothing and let the trolley continue on track B, which has the same number of people on it as there are real numbers. Both of these quantities are infinite. So which one do you choose? The answer might surprise you. Hey guys, it's PT, math musician. That's right, today we're going to tackle the infinite trolley problem. Now, in case you don't know, the so-called trolley problem is a moral dilemma created by English philosopher Philip Foot in 1967. In this scenario, a trolley with no brakes is about to run over 5 people, but you have the option to switch it to a track containing only 1 person. Now, I've seen a lot of different spin-offs and other versions of this moral dilemma, but a few weeks ago, some friends of mine showed me this version that I had never seen before, and they thought it would make a good topic for a math video. So let's really quick go over the problem one more time, and then we'll get into it.
Do you pull the lever, killing 1 plus 1 plus 1 plus 1, etc. people, 1 person for every integer, resulting in infinite people dying? Or do you do nothing, allowing the trolley to kill 1 person for every real number? In both cases, infinitely many people die, but in the top case, the smallest possible infinity of people die, Alice not, whereas in the bottom case, a larger infinity of people die, some infinities are bigger than others. What do you do?
Okay, so first of all, let's be clear that you can't jump on the trolley and hit the brakes, and you can't take anybody off the tracks. That's cheating. Now, our approach to this problem, beyond this, depends on whether we think of it as strictly a theoretical trolley problem, or if we think of it as potentially happening in real life, and therefore incorporating the laws of physics. So we'll look at both of those, starting with physics. So, if we allow for real-world physics, then we should take the engineering approach and say, well, it looks like... Hold on, let me get my reading glasses on here. It looks like track B has the people much tighter together, so we should probably send the trolley down that way so that she'll eventually be stopped by the friction and dead weight caused by the rapid accumulation of bodies. Yeah, it's pretty morbid to think about, but the fact is, that would result in only a finite number of deaths, because the trolley would eventually stop, whereas track A, where the people are more spread out, probably would not force the trolley to stop, and would therefore kill infinitely many people. So, if the laws of physics apply, then you should actually pick track B in order to cause the least number of deaths. There, I made all the engineers out there happy by answering the problem practically. But now we're going to do what we're really here to do. We will use traditional trolley problem logic and assume that everything on the chosen track gets obliterated. And this is where we need to take a step back and look at a tricky topic in theoretical mathematics: infinity. So the problem tells us that track A has 1 person for every integer, which are positive and negative whole numbers like 0, 1, 2, 3, negative 500, etc. On the other hand, track B has 1 person for every real number. Now, the real numbers are comprised of the rational numbers, which can be represented as a fraction, like 0, 1, 1/2, negative 77/5, and the irrational numbers, which can't be represented as a fraction, pi, e, square root of 2, etc. So one way to look at this visually is if we have the real number line here before us, all these tick marks that are the whole numbers, those are the integers. But the real numbers take up that entire solid line. So like the entire spectrum. They include these, but they also have every little thing that's in between them. In other words, the integers are isolated units, but the real numbers are on a continuum. So there are infinitely many integers and infinitely many reals. But how exactly are these two infinities different? The short answer is the integers are countably infinite, but the reals are uncountably infinite. So let's break both of those down. So before we talk about countable infinity, we first need to understand a couple of terms: natural numbers and bijections. Now, the natural numbers, or as we often call it, the set n, capital N, is the set of all positive whole numbers. So 1, 2, 3, 4, all the way on up. The regular counting numbers, basically. Now, a bijection between two sets, let's just say A and B in general, is a mapping of the items in each set that is both one-to-one and onto. So what that means is we're basically matching up the items in A with items in B, and it has to be a matching so that each single item in A matches with exactly one item in B. That's what one-to-one means. Each one pairs with only one. And it's onto, and that just means that no items are getting left out. So there's nothing in either of these sets that's going to be left uncircled or unmatched. So that's a bijection. All right, now we're finally ready to properly define countably infinite. So in general, a set A is countably infinite if it is possible to form a bijection between A and N. Now remember, N is just the natural numbers, so 1, 2, 3, 4, and onward. And if we can form that 1-to-1 and onto matching up, if we can pair off the items, then that means that A is countably infinite. And if you think about it, that kind of makes sense, because literally what that means is we're counting the items in A. We're saying 1, 2, 3, 4. That's literally what you do when you count things. So even though they go on forever, we can still, in a sense, count them by pairing them off with the natural numbers. So that's what countably infinite means. Now, I know that was a lot of technical terms, but to see an example of how this works, we're going to show that the set E of all even positive integers is also countably infinite. And now don't miss this, because what that means is that there are just as many even numbers as there are positive whole numbers altogether. So like if you take the set of even numbers and odd numbers together, there's actually just as many of those as if you were just looking at the even numbers. Now, of course, you might be thinking, wait, what? There's only half as many even numbers. Yeah, well, watch and see. Because remember, we're talking about infinity, so things are not always as they seem. Alright, so we're trying to prove that the set E of all even numbers is countably infinite. And the way we're going to do that is to find a bijection that goes from the natural numbers to the even numbers, from N to E. And visually what that looks like is we're trying to find a way to match up the items in the natural numbers with the items in the even numbers in such a way that it's 1-to-1, which means that each item maps with exactly one item and vice versa, and it's onto, which means nothing gets left out. So consider the function f from N to E, defined by f of n equals 2n, that means just 2 times n, for every n in the natural numbers. So we're creating a function that takes inputs from the natural numbers, 1, 2, 3, 4, general input is the letter n, and it doubles it, forcing it to be an even number, so our outputs are all even numbers, 2, 4, 6, 8. So like f of 1 is 2, f of 2 is 4, f of 3 is 6, and in general, f of n, for any natural number n, is 2 times n, which is in the even numbers. So now we just need to show, is f a bijection? Which means, can we show that it's 1-to-1 and onto? So that's what we're going to do next. So the first thing we need to figure out is f 1-to-1? So the way we're going to show f is 1-to-1 is we're going to show that equal outputs from E mean equal inputs from N. And the reason I'm going to show that is because if equal outputs means equal inputs, then that means it's impossible to have two different natural numbers that map to the same even number. And if we can show that, then that means it's 1-to-1. So we're going to take two random outputs from E. Remember, these are all even numbers, so under f, they all appear as 2 times some natural number. So we're going to say 2n1 equals 2n2 for just two random outputs, but we're saying that they're equal to each other. And when you do that, you can do a little algebra and divide out the 2's. The 2's cancel, and you're left with n1 equals n2, which means that the inputs from n were equal the whole time. So yes, we've shown that equal outputs mean equal inputs, and therefore f is 1-to-1. And finally, we need to show that f is onto. Now, by definition, what it means to be an even number is that you can write it as 2n for some positive whole number n. And therefore, since that's literally what our function f is doing, that means everything in the even numbers is mapped to under f. And that's just a fancy way of saying that nothing in E is left out when we apply our function. So, we've shown that our function f from n to E is 1-to-1 and onto, and therefore it's a bijection. And so since we've shown that there is a bijection from the natural numbers to the even numbers, that means the even numbers are countably infinite. And QED, we are done. And by the way, this is a good way to understand why we can't have any smaller infinity than that of the natural numbers. Any pattern of selecting only certain ones, like we just tried to do with the even numbers, is still going to amount to the same thing as the total number of whole numbers. Now, I technically shouldn't say the number of whole numbers because that's infinite, and infinity itself is not a number. So instead, what we use in the math world is this symbol called aleph naught to represent the size of the natural numbers, which is also the size of any countably infinite set. And as we just said, that is the smallest possible infinity, aleph naught. Okay, so now in a similar fashion, we're going to prove that the set of all integers, which is positive and negative whole numbers, including 0, is countably infinite as well. Alright, so I'm going to try to go through this proof a little bit faster since you've seen how the general process works in the easier case of the even numbers. So this time we're trying to find a bijection from n to z. Now n again is the natural numbers and z is the integers. So positive and negative whole numbers and also including 0. That's the integers. So we choose a function from n to z defined by f of n equals, there's one of two choices. If n is even, then our function, our output is going to be negative n over 2. And if it's odd, then our function output is going to be n minus 1 over 2. F of 1, well, 1 is odd, so we put it down here. So that's like saying 1 minus 1 over 2, which that comes out to 0. F of 2, well, 2 is even, so we go up to the top case. That's the 2 goes in there and it becomes negative 2 over 2, which is negative 1. F of 3 is positive 1, F of 4 is negative 2, F of 5 is positive 2. You can probably start seeing the pattern here, is that we're flipping back and forth between whether we're assigning our natural numbers to the positive integers or to the negative integers. And of course, we cover 0 in that initial case. So that's what our function f is doing, is f 1 to 1. So suppose f of n1 equals f of n2. That's like saying we're just given two random outputs, but we're saying, what if they were equal to each other? And if we can show that that means that n1 and n2 were equal the whole time, then that means our function is 1 to 1. We have three possible cases when we say that the outputs are equal. They're either both the top case, both the bottom case, or one and the other. So we're going to address all three of those cases. So case 1, both of our outputs were the top case in how we defined f, which means negative n1 over 2 equal to negative n2 over 2. So those are our two outputs. Well, similar to last time, we can just do some simple algebra and we're left with n1 equals n2. So yes, we do have equal inputs in the first case. All right, now case 2 is what if both of the outputs were the bottom case, like when n is odd? Well, again, some very simple algebra allows you to cancel the 2's from both sides, and then you add 1 to both sides, and those cancel as well. So you end up, again, with n1 equals n2. So case 2 is also good. And finally, we have our third case, which is what if 1 was the top case and 1 was the bottom case? So it's like if one of them was odd and one of them was even. So again, we do some algebra. We can cancel out those 2's, and then do some change sides, change signs, and get all the positives over here, and then that becomes a positive 1 on that side. n1 plus n2 equals 1. Now you might think, oh no, we've failed to show that n1 equals n2. But here's the thing, this statement right here is literally impossible because these are both positive whole numbers, which means that they are 1 or more, and it's impossible for two positive whole numbers that are 1 or more to add to equal 1. So case 3 is literally impossible, so we just ignore this case. And that means that we've shown all the cases that actually matter do show that f is 1 to 1. So given an integer k, a random integer, if that's a negative number, well, let's let our n from the natural numbers be negative 2k, an even natural number. Then f of n, which is like saying f of negative 2k, well, when you put that in, that becomes the top case when n is even. And so you're saying negative 2k over 2. Well, the negatives and the 2's cancel and you're left with k. So that works. So that random integer that we were given was able to be mapped to under f. And similarly, if k is positive or 0, then consider n equals 2k plus 1, which is an odd natural number. Then f of n, which is equal to f of 2k plus 1. Well, that's the bottom case, which means we're plugging it in here. So we get 2k plus 1 minus 1 over 2. Again, the plus and minus 1 cancel, and the 2's cancel, and you're left with k. So once again, we've shown that that random integer can be mapped to under f. So everything's covered. Every integer is covered under f. So it's onto. And therefore, since we've shown that it's 1 to 1 and onto, f is a bijection, and therefore z is countably infinite, QED. Cool. So now we have a very thorough understanding of what it means for something to be countably infinite. Aleph not. The same number as there are integers, which is also the same number as there are natural numbers. Now, what about track B, which has the same number of people as there are real numbers? Not natural numbers, not integers, real numbers. Well, I've already stated that this quantity, unlike the first one, is uncountably infinite, which means you can't form that bijection with the natural numbers like we were talking about a minute ago. And I would show you the proof of this fact, but it's a little bit too long and complicated for this video. However, I'll at least try and explain why the reals are uncountable. So again, when we say that a set is uncountably infinite, that means that the set is infinitely large, but it's impossible to form a bijection from the natural numbers to that set. Because think about it, what if you were to try to pair these off and make a bijection so that you could use the natural numbers to count the real numbers? Well, let's start with pairing off the number 1 from the natural numbers with, let's say, 0 for the real numbers. Well, what's the next number? Think about it, what is the next number in the real numbers? Like, what are we going to pair with 2? That's a tough question because, well, we can't just go to 1, right? Because we're missing everything in here. Because remember, the reals do include the integers, all the positive and negative whole numbers, including 0. The reals include those, but they also include every little thing in between. Fractions, infinite repeating decimals, irrationals, and therefore there's no way to find 2 numbers that have nothing in between them. So let's say instead we tried to only find a bijection with the natural numbers for the range from 0 to 1. Let's say we only focused on that. Well, then even still, we would pair off the 1 with the 0 and the 2 with, well, what's going to be next? Well, it can't just be 0.1, right? Because we also have 0.01, 0.001, 0.0001, and everything in between. See, no matter how close we get to 0, no matter how much we zoom in, we can't find what our next number should be because there's always more numbers that are still in between those. You're always going to miss something if you're trying to pair them off with the natural numbers, because there's no spaces, it's all just one continuous line. In fact, any 2 numbers in the reals that we could choose actually have uncountably infinitely many more real numbers between them. That's insane. So if track B has uncountably infinitely many people on it, then if you take any 2 people, even 2 that appear to be right next to each other in the picture, then you can actually fit all of the people on track A in between those 2 people on track B. Isn't that crazy? So maybe that'll help you wrap your head around just the sheer magnitude of how different these 2 infinities are, just jumping from countable to uncountable. It's insane. So if you thought track A would result in a lot of deaths just by being infinite, it's still practically nothing compared to the massacre that we would be committing by running over uncountably infinitely many people. Oh, okay, well, that settles it then. We should just switch to track A and only run over countably infinitely many, right? No, absolutely not. But, come on, there's obviously more people on track B. Or is there? Turns out there's something else going on with track B that we need to look at. This problem is assuming that it is theoretically possible to have uncountably infinitely many people. And even in this purely hypothetical scenario, that is nonsense. Now, before you guys get in the comments like, PT, you're so stupid, it's just a fictional problem and it's okay to be hypothetical. Look, I know, okay? I know it's just a pretend situation. Come on, we're talking about infinitely many people tied to a trolley train track, for crying out loud. What I'm saying is that the concept of uncountable infinity, by definition, cannot be applied here. It would be like if I asked you, hey, just hypothetically, how many hours are in a mile? Just hypothetically. I know it's not realistic, but like in a hypothetical scenario, how many miles would be in an hour? Or how many hours would be in a mile? I can't remember which. But you see, you get the point. These 2 ideas are definitionally incompatible. Yeah, is that a word? Definitionally? Oh, it is. Look at that. Definitionally incompatible. There you go. Okay. So think about it. Sorry, I'm starting to lose my voice here. In order for something to be uncountable, it needs to be impossible to form a bijection with the natural numbers. But these are people we're talking about. We don't exist on a continuum like the real numbers do. Even if you have infinitely many, theoretically, you could still count them because, there's also infinitely many natural numbers to go around, so you can just keep pairing them off. Probably the most obvious systematic way to do that is to have everybody line up single file and then just start assigning each one a natural number. So since we can count them systematically like that, then even if they are infinite, they are still only countably infinite. Which means, now this is important, don't miss this, which means that the highest number of people that you can ever, even theoretically, have is Aleph naught, countably infinite. So, unfortunately, this trolley problem is lying, or sadly mistaken, about the quantity of people on track B. That's right, we can slap a big old question mark onto track B. So, we now have two options for what the actual status is for track B. Option 1, it has a certain finite number of people on it, in which case then that is obviously the right track to pick, since it has strictly less people than track A, which again, we've already established that to have infinitely many people. Option 2, track B also has infinitely many people on it, which is then, again, forced to be Aleph naught equal to track A, in which case it really wouldn't matter which you chose because they have the same number of people on them anyway, so we arbitrarily stick with track B. And therefore, bringing it all together here, ignoring the laws of physics and using traditional trolley problem logic, amazingly enough, the correct way to cause the least amount of deaths possible is to still go with track B. So if you thought the answer to this problem was going to be track A just because it appeared to have fewer people on it, you were wrong. In fact, you were actually, whether you realized it or not, you were actually opting to cause the greatest amount of death possible by picking track A. How dare you? Ah, come on, PT. The highest number of deaths? I mean, it's not like I asked you to go down both tracks at the same time. Okay, but this actually does bring up a really interesting aspect of infinity. This is where it gets really trippy, so humor me for a second. If you were to theoretically go down both tracks, you really are going to run over just as many people as if you had only gone down track A, which has countably infinitely many people. Think about it. If track B has only finite people on it, then even if it's a massive number, like 1 million, if it's some fixed number, well then that doesn't really add anything to track A if we're combining those two together, because A is already infinite. Aleph naught plus 1 million is still Aleph naught. So any finite number of people on track B would actually leave the kill count from track A unchanged if you were to put them two together. Okay, fine. But what if both tracks have countably infinitely many people on them? Surely if we add two infinities together, then we end up with some larger infinity, right? Wrong. Aleph naught plus Aleph naught is still Aleph naught. That is to say, the union of two countably infinite sets is also countably infinite. And if you don't believe me, we're about to prove it. So let A and B be countably infinite sets, and that means that A has infinitely many elements, but we can count them, so we're going to label them A sub 1, A sub 2, A sub 3, and similar with B, we're going to name the elements in that set B sub 1, B sub 2, B sub 3. We're trying to find a function that can be a bijection from the natural numbers to A union B, this symbol that looks like a U here. In the math world, that means union. It's like putting all of these and all of these together into one set. So we define our function f from the natural numbers to A union B by f of n equals, so you take a natural number n as your input, and your output is going to be one of two choices. Choice number 1, if n is even, then you're going to map it to b sub n over 2. That's the element that gets paired with. Similarly, if n is odd, then it gets mapped to one of the elements of A, specifically A sub n plus 1 over 2. So basically what our function f is doing is it takes the natural numbers, and if it's odd, it sends it to one of the items in A, and if it's even, it sends it to one of the items in B. Specifically, the natural number 1 would map with the first item in A sub 1. The natural number 2 would map to the first item in B sub 1. 3 maps to A sub 2, 4 maps to B sub 2, and so on and so forth. Even though those are two infinite sets, by following this pattern, well, we're never going to run out of natural numbers to pick from, so we can always just flip back and forth and eventually hit every single thing in each of these sets. So f is a bijection. And this time I'm not going to formally show that it's one-to-one and onto because it's a little bit too complicated to do here. But suffice it to say, you can see here how it works and how it pairs everything off and doesn't leave anything out. And therefore, we have shown that the union of these two countably infinite sets is also countably infinite. So really, no matter what's happening with track B, if you send the trolley down track A, then you've actually committed just as much of a massacre, that is, causing Aleph naught deaths, as if you had gone down both tracks. Interesting. Anyway, enough with multi-track drifting. Let's get back to the actual problem. Okay, so let's do a quick summary. So far, we have shown that if you allow for the laws of physics and assume what we see in the picture is accurate, then going down track B would cause the fewest number of deaths. Likewise, if we ignore physics and assume everything on the chosen track will be obliterated, you should still take track B, because based on the misapplied math in the given question, we don't know for sure if B has infinitely many people or finite, whereas we do know for sure that track A has infinitely many people, and therefore has the highest number of people even theoretically possible on it. So obviously we can't pick track A. Well, okay, great. So we should just take track B no matter what. And that's the answer. Right? Well, okay. Before we conclude our answer, there's one last crucial aspect of the problem to consider, and that is morality. Specifically, we need to talk about something called utilitarianism versus deontology. A person with a utilitarian view of morality is concerned primarily with results. They determine their actions by what will cause the most favorable outcomes for the most people. It's sort of a needs of the many outweigh the needs of the few situation. But a person with a more deontological view of morality is more likely to determine if an action is right or wrong strictly by the action itself rather than its result. Do you remember the original trolley problem that I talked about briefly at the beginning of this video, where you had 5 on the oncoming track and then you had the option to switch it onto a track with only one person? The whole point that made that a moral dilemma was not strictly about, oh, should one person die or should 5 people die? No, it was about seeing how different people would respond based on whether they were more utilitarian or deontological. A utilitarian would probably say, flip the switch, it's better to save the 5 people than the 1. But somebody with a more deontological morality would probably say, no, let this train keep going, because if you pull that switch, then you're doing an action that directly causes someone to die. Whereas if you just let the train keep going and kill the 5 people, then you were hands off and you didn't really do anything. When I first analyzed this problem and started figuring out how I would make it into a video, I assumed the utilitarian approach of choosing the outcome that would, result in the fewest number of deaths. And that's kind of how we've been approaching the problem so far in the video. But I do think we should be true to the original trolley problem as a moral dilemma and ask ourselves, how would a more deontologically based person solve this infinite version of the trolley problem? Well, it's really not that hard to figure out. If we assume that this is a person that would choose to leave the switch alone and let the 5 people die in the original trolley problem, with the knowledge that flipping the switch would kill the people on track A, which is Aleph Naught, literally the highest death count even theoretically possible, then they would clearly choose to stay hands off and let the trolley continue on its current path, killing the unknown, and therefore less than or equal to, amount of people on track B. And the interesting thing is that both schools of moral thought actually agree in this situation. The deontologist is happy because they don't commit a direct action that causes death, let alone the death of infinitely many people. And the utilitarian is happy because it results in the best outcome for the most people, namely an outcome that involves equal or fewer deaths than if the switch had been flipped. So, at the end of the day, whether you allow for the laws of physics or not, and whether your ethics are more utilitarian or more deontological, the best thing to do in this crazy, outlandish moral dilemma of infinities is to simply let the trolley continue on its course on track B. Even though we don't know how many people we have doomed by letting the trolley stay on track B, what we do know for sure is that we are simultaneously saving the infinitely many lives on track A. And that, my friends, is the infinite trolley problem. Thanks so much for watching the video, guys. If you enjoyed it, please give it man. Sorry. Man, I haven't talked so much straight since I gave my capstone project before graduating college. Oh man, that was a time. I think I was wearing the same shirt too. It's crazy. I guess this is my math teaching shirt. Anyway, if you enjoyed the video, please give it a like. Subscribe to The Math Musician if you haven't already. I know this is the first, actual full math video, but hopefully it'll be one of many. It's a lot to work through, and I know it's been a long time coming, but thanks for your patience. And, yeah, I hope you enjoyed it.